In this video, I want to show how to apply Newton's method in Python. And I want to apply it starting at the root estimate -1.5 for the polynomial x cubed minus 2x plus 2. So let's start out defining the function represented by this polynomial in Python. So let's use a lambda function. So lambda x, input is going to be x, output is going to be x cubed minus 2 times x plus 2. And to apply Newton's method, we also need the derivative of f. And you might think we're going to find that in some fancy way, but instead all I'm going to do is look at this polynomial, see what the derivative is, and define a new function that is that derivative. And I'll call it df, but you can call it anything you want. This is just to remind me that it's the derivative. And again, input is going to be called x, and then output is going to be 3x squared minus 2. Okay, so 3 times x squared minus 2. And how does Newton's method work? Well, if you give it some x value, like -1.5, then it outputs x minus f of x divided by f prime of x. So let's write a function that does that, and let's just call it newt. Again, it's simple enough. I can use a lambda function. And I think instead of x, I'm going to call it z, okay, just because I'm going to think about it a little differently. And so this will be z minus f of z divided by f prime of z. And Jupyter Notebook is doing me a service by showing me I wrote the wrong thing here because it's showing up in this weird color. Yeah, I really wanted to do df. Okay, great. And so, I just finished recording another version of this video, and I got through the end and I realized I never actually did what I promised to here. I never actually applied Newton's method 3 times. So let's go ahead and do that. So we're going to apply it 3 times, but so that I can change that to a bigger number if I want, I'm going to use a variable for it. Let's call it reps. And let's define, it'll be a one-dimensional array. And let's just start out with zeros of length reps plus 1, because it's going to have the original value -1.5, and then these like 3 iterations of Newton's method. Okay, so I can do ARR bracket 0, set that equal to -1.5. Okay, so maybe I'll set z equals -1.5, and then set this equal to z. Okay, so if I look at ARR, this one is meaningful. The other ones are just placeholders. Maybe I'm going to fill them in. And so then for I in range reps, I want to do something 3 times, or reps times. So that's I can't think of a good way to avoid the for loop here. So I'm going to do this using a for loop. And this we'll go through this for loop 3 times. And so what do I want to do? Well, I want to say ARR brackets I plus 1. Okay, so for example, we're going to start with I equals 0, and then we're going to fill in this with the Newton method approximation. So that's going to be newt of, and then newt of what? Well, it should be whatever the previous value was. So it'll be newt of -1.5 to start, or in general, it'll be ARR bracket I. Okay, and then let's look at ARR. Okay, perfect. And just as an example, if I were to do newt of -1.77282.692, okay, I should get something very close to this value. Okay, yep, very close to this value. Okay, excellent. And so that's already finishing what I promised to do here in this video, but let's also take a quick look at the graph of f of x so that we can see kind of where these numbers are coming from. So big X equals plt.subplots. And then for my x values, let's use a few more than usual. And I'm starting at -1.5, and I definitely want it to contain all of these numbers. So let's go -2 to 2 with 1,000 sample points. And then let's do not PLT dot plot, even though that would work. Let's do x dot plot, x. And then what should the y values be if I'm trying to plot this function f of x? Well, the y values should be f of x. Okay, great. And maybe I'd like the style to look a little different. So let's use one of those styles from a previous video. Let's do plt.style.use, and let's use Seaborn Dark Grid. Okay, part of the reason I like that better is now I can see this white line at y equals 0. And so what we're doing is we're starting at -1.5, we're drawing the tangent line, and then we're seeing what is the root of that tangent line. Okay, like what's a root of the linear approximation? Then where does that root occur? It occurs at approximately -1.84. So then we're drawing another tangent line at -1.84 and seeing where that tangent line crosses the x-axis. Okay, and in that case, it's -1.77. And hopefully we're getting closer to this. Hopefully we're getting closer to the actual root, okay, which is here. You can see that that's the only root of this cubic polynomial. And so let's see if we're actually getting closer. So I want to apply the function f to all of these. And because it's a NumPy array, I can just do f of that NumPy array. And yeah, that's looking pretty good. For example, this is -6.6 times 10 to the -5th. Okay, so that's getting really close to an actual root by the time we've done our 3 iterations of Newton's method. Okay, that's where I'll stop this video. Thank you for watching.